So maybe then I'll pass it to Tim.
And I'll pass it to Kelly. Go ahead and share your screen.
Okay, thanks. Okay, so just double checking that the screen looks okay, is in presenter mode.
Looks good.
Yes, it looks great.
Okay, great, thanks. Well, I'm excited to be here today to talk about NEIVA. My name is Kelly. I am a scientist at NCAR in ACOM. I've been here just this time for 1 year, just over a year. Previously, I was a professor at University of California, Riverside. And my co-authors on this work are a graduate student from UCR, Samiha Binte Shahid, and Christine Wiedenmeyer and Bob Yokelson. Because my talk is a bit different than what I saw yesterday, and I'm new to many of this community, and just in general, the body of work that I'm doing is new. So I've taken a few slides, less than 10, to talk about some background motivation and like the genesis of NEIVA. I do want to point out that right now, NEIVA exists in its current iteration as basically a collection of emission factors. So although the word emission inventory or the term emission inventory is in the title, we're not really a true emissions inventory. Hope to grow into that space, but right now we're just a series of connected data tables. But I'll talk about structure, contents, comparisons with other sets of emission factors, and some of the sort of implications in the context of atmospheric chemistry and predicting smoke from fires. Okay, so one of the things that I think is probably familiar to most people on this call, right, is that the emissions of PM 2.5, so fine particulate matter, organic carbon, and black carbon, are highly variable across fuel and fire types, right, and depend on combustion conditions as well, soil moisture, fuel moisture, et cetera. This is just a snapshot of some organic carbon and black carbon emission factors. These figures are illustrative of the ecosystem that these fires were sampled in, and this one column here is wildfires. So we have temperate forest wildfires and prescribed burns, and then prescribed burns in another set of ecosystems here. And the point really that I wanted to make here is that organic carbon emissions are higher in wildfires than prescribed burns, right? This is also something that's pretty well understood. But in addition, that organic carbon, right? So for most fire types, including an expanded list that aren't shown here, most of this fine particulate matter is organic, right? So for the fires and fire types shown here, about 75 to 90% of that fine PM is organic. So that's important. The other thing that I want to talk about real quick is that, you know, organic carbon partitions between the gas and particle phases, right? And this really influences the spatial and temporal distribution of PM 2.5. So one way to think of this is if we're following a plume in a plane, for example, a lot of times when we look at the emission ratio of PM, we see something that's like roughly steady, right? So we account for dilution and we see that the PM 2.5 mass doesn't change a whole lot. I mean, you know, over some time and distance, of course, over large scales, this can change. If we think about just the emissions, right? So if we have just primary emissions, we would have dilution, right? So, and in that case, we have dilution and we have that then follows subsequent evaporation. And that really leads to a decrease in PM 2.5 mass and time. The other thing that can do this is, of course, heating. I didn't talk about this, but if the PM 2.5, if the plume is heated, right, we can get evaporative emissions as well. On the other hand, oops, what's happening? Oh. Okay. On the other hand, right, we can have an increase in that PM 2.5 mass and time, and that is due to chemistry, right? So this basically we have this chemical conversion of the gas phase PM 2.5 or aerosols, if you will, to particle phase PM 2.5 or organic carbon during plume evolution. And it's particulate matter. It's really not fair to say gas phase PM 2.5. It's really better to say gas phase aerosols, but just to sort of be consistent with the terminology here. But the bottom line is we have this conversion between gas and particle phase organic carbon. It changes the concentration and composition, and really that influences the health and climate effects. So I want to say that this has really been a driver for the focus, my focus on the non-methane organic compounds, both in the gas and particle phase, but largely in the gas phase. Okay, so with that, I'm giving you a quick overview of the research in my group that really led to NEIVA. So if we think about this, overarching goal, right, this is just showing this, this is from 2021. We have these fires in Western US, smoke is transported over the east, right? We had terrible air quality conditions in the eastern US. So we want to be able to predict these events, the composition and concentration of smoke in different areas. And so when we started out, one of really the big questions was what compounds are actually being emitted from smoke? And again, focusing on this gaseous non-methane organic carbon. And at that time, there are probably a couple papers out. Bob Yokelson had one, 2013, Karsten Warnecke, I think it was I think they're both around 2011, 2013. And then we're saying that we can identify about 50% of the mass of organic carbon. So, from this chemical perspective, if we're trying to predict atmospheric chemistry of the emissions, right, only being able to identify 50%, right, we have a gap and there's a lack of understanding. We can't predict what will happen if we don't know what's being emitted. So really, that's where I started this work. Then we started thinking about, okay, now that we're measuring all these compounds, what do they do? And how do we represent this complex chemistry in simplified models? And then really more recently, I've been thinking a lot about how we make these data, like the wealth of data, more useful and accessible. So really all of this culminated in NEIVA and is still a work in progress. And NEIVA stands for the next generation. I didn't read this through, I think, on my title, but it's the next generation's emissions inventory expansion of IGAC. And for those of you that aren't familiar with IGAC, I would call this sort of the state of the science emissions database about 10 years ago. Okay, so if we dig in a little bit more, right, any good bit of research leads to more questions than answers. So I want to just say that one of the things that we found when we started out on this journey is that the non-methane organic carbon emissions were highly variable as a function of fuel type, and I think even component. And by component, what I mean is that we saw huge differences in emissions profiles, and largely in lab, but we saw this in the field as well. When you combust litter and soil and canopy versus when you just have litter consumption. And so one of the things that's been discussed, and I totally agree with this, is that when we're looking at PM 2.5, when we're looking at total non-methane organic carbon, or non-methane organic compounds, one of the biggest bits of uncertainty is certainly fuel loading and composition. And I've seen this in many publications and in my own work. I will add the caveat that when you start really looking in the weeds at these detailed non-methane organic compounds, I think that the picture changes a little bit. So I just want to point that out here, since it's been something that's talked about. So just for example, right, when we measured, two coniferous species, pine trees and spruce, we see huge differences in the dominant monoterpenes. So number one, monoterpenes are one of the largest categories of NMOC emissions. And then second, we saw really big compositional differences. And these two compounds behave very differently in the atmosphere. And one, for example, has a much higher SOA formation potential than the other. Okay, so this is a challenge, right? Complexity is a challenge. The other thing is that, this was presented yesterday, right? Typically, these fuels are represented by a limited number of fire types. They have to be. And that number really depends on model scale and complexity. Whereas we were largely measuring individual fuels, right? We started out in the lab. Again, we've done field work as well, but we started out in the lab. So there's a gap, again, the space that we have to cross to provide useful information. The other thing is we were really proud of all the work that we had done, right? We have all of these compounds lists, but they weren't being used by modelers. And those of you that are, regional global modelers are like, of course, we didn't use your list of 700 compounds. And you know, one of the reasons, if you're not familiar with how gas-phase chemistry or secondary organic aerosol is predicted in larger scale models, right? Typically, these processes are represented by less than 10 model surrogates, right, or representative compounds, and not 700 individual compounds, right? So, for example, we measured 38 different monoterpenes. Again, this category of compounds, they have orders of magnitude differences in their atmospheric lifetime, but they're represented sometimes in model by a single compound. So this presents a challenge for us. We were not the only ones out there producing data. So we participated in Flame 4 and FireX. There were a number of other field studies that have happened over the last recent history. And I will say that I am just highlighting those in the US. There, of course, have been many other studies globally. Namaste is one example off the top of my head. So one of the other challenges, again, so a bunch of good data, but one of the challenges that this presents is that we have a bunch of disparate data sets, right? And they're very difficult to compare and integrate. And when any new list of compounds, what I saw when it was being used by modelers, it was a single list, right? So you take one new set of emission factors from one paper, and you may apply it to a single fire, right? So there isn't really this widespread or easy way to take advantage of the data that are out there. So that's really where we started with NEIVA. So to move into a little bit now, what is NEIVA? What are the structure and contents? And I just want to say that I cannot see my chat or anything. So if I need to be interrupted at any time, please feel free, hop on in and let me know. Okay, so okay, so this is a schematic of NEIVA, and I'm going to go through these parts in a little bit more detail. So I apologize if, depending on the screen that you're using, if this is a little bit hard to see. But basically, what we have is we have a collection of linked databases, right? This is what I was saying before. So we did data collection. We parsed this data into 2 different databases that I'll talk about a little bit more in the next phase. We have 2 data processing steps. So we had one data processing step here where we've joined and formatted and combined all of these data into this primary database. We have a data integration step, and then we end up with an output database that has several data sets in them. We have finally this recommended set of emission factors. So again, I'm going to talk about these a little bit more, but again, basically we have 2 data processing steps. And one of the unique things I think about this database, the NEIVA database as a whole, is that we are linked. We link the database to chemical mechanisms and properties. And so what I mean by this is that the individual non-methane organic compounds that are in this database also have associated chemical and physical properties like Henry's law constants, vapor pressures, O to C ratios, and other things that are important for understanding atmospheric chemistry, fate, and transport. In addition, to make these data more usable, we mapped the thousands of non-methane organic compounds to model species. And we just chose 3 sort of widely used chemical mechanisms: SAPRAC, Mozart, and GeosChem. Okay, so a little bit more about what each of these sets of tables, right? So database is really a set of tables. So in the legacy database, this is the Akagi 2011 paper. So all of the data that were in 2011 are in this legacy database, as well as updates that happened in 2014 and 2015. The data are organized in tables. We have 14 tables, 1 for each fuel or fire category. We made some changes to the fuel and fire categories. These are described in the forthcoming publications. I'm not going to go into those. I don't have time here. The other thing we did then, the other data collection are now new data that are not included in Akagi, right? So publications from 2015 or later. These include field studies and selected laboratory studies. And I keep losing count because this paper has been taking us a while, and so we keep adding papers, but I think we've added data from 38 publications since 2015. Then we put all this together. So we have these data reformatted, they're in a consistent structure, and we have 44 tables in this repository. So this is now all of the data that we've gathered. So one of the important things is we really wanted for this data to be queryable in different stages. So some people might just want one recommended set of emission factors for temperate forest or for peat. On the other hand, someone else might want to compare all of the ponderosa pine laboratory studies. So we really have this so that all of these databases or data sets are queryable. The output database is now 3 data sets. So it's the integrated EF. So between the primary database and the integrated EFs, we did some data processing. And then for this last step to get to these recommended EFs, we did a lot of data processing, okay? And then this is the database where we have this physical, chemical, and thermodynamic property data and the surrogate model species assignments. And these are all linked by unique IDs. So this is just an example, again, to help you get your head around. And what I should say now is that I'm going to apologize in advance for the large number of tables that are forthcoming, but it's really the best way to illustrate what the contents of NEIVA are. And then we'll get into some figures where we're comparing. But these are the tables in this legacy database, right? So these are all of the fuel or fire types that were reported in the IGAC paper. We've made a few minor changes, and we've mapped or separated or categorized is the best word actually to say all of the pollutants into one of 5 categories. So we have individual organic gases, we have methane, we have non-methane organic compounds in the gas phase, and then we have PM and PM constituents. So PM constituents would be organic carbon, for example, or PM 2.5 or PM1, right? So we have, you're classified as either PM, non-methane organic gas, methane, inorganic gas. We also have non-methane organic compounds in the particle phase, but none of that data were available for this IGAC paper. This is a sample now of the raw database. So these are the new papers. So you can see we have the fire or fuel type. So we have things like savanna, boreal forest, tropical forest, right? The same fire types as IGAC. Some of these papers, especially the lab studies, report multiple fuel or fire types. So we have a collection of those. These are examples of some of the papers, the pollutant categories that I just introduced, the source data, where the data came from in the source publication and DOI. So all of this information is stored in the raw database, so everything is highly traceable. We really wanted to keep lab studies or include lab studies. So some of you are aware of the most recent emission factor compilation by Andy Andre. And in that study, right, it's only field studies. And there is a lot of discussion to be had about the pros and cons of lab studies. But one of the things I've sort of separated a couple pros and cons here, right? The field studies are hugely important because you have real fuel mixtures and real fire behavior. But from, again, this chemistry perspective, there are much fewer compounds that have been identified, and the age of smoke is really harder to define. And this was brought up yesterday, this idea that emission factors changed in time, right? So depending on where and, by correlation, when you measure emissions, you get different values, and trying to reconcile that, I think, in model input and then subsequent calculations is challenging. So, what is time zero? The lab studies are tricky because you have individual fuel species and components. You have well-controlled burn conditions, but you typically have more flaming and less smoldering. This, of course, does depend on the study. But again, pros are that you have many compounds identified, many more that have been identified in the field, and the age of smoke is well defined. So we wanted to keep these individual fuels that have been measured in lab studies, and this is just an example of how we mapped these individual fuels to these fuel or fire types, right? So we have both the emission factors from all of these individual fuels, as well as we've mapped them and come up with some final or recommended EFs in each of these categories. Okay. Okay, so one of the critical development pieces here was assigning unique IDs to each non-methane organic compound or group of compounds. This, when I mentioned earlier, this idea of disparate data sets, right? So one of the problems is that we, for anyone that's worked with organic compounds, we all have, our own names for them. And then a lot of times when we report data in a publication or even upload to some website, the naming convention gets a little crazy. And a lot of times we also, especially if we don't have a unique name for the compound that's been identified, we might label it according to the analytical technique that was used. So it's often really hard to compare sets of emission factors. So we spent a lot of time trying to figure out how to assign unique IDs to these compounds. So Samia came up with an algorithm, and basically we had this hierarchical naming structure. So we started with IUPAC International Chemical Identifier. So we assigned an INCHI if we could. The second thing, we have exact or protonated mass as reported in the source publication and chemical formula. This is the case when we have lumped compounds or an unknown structure and identified by, for example, FTIR and PTRMS, right? So these would be the analytical techniques, right? So you can't assign an INCHI to lumped compounds or something if you don't know the structure. We have two-dimensional gas chromatography data. So in this case, we assign names based on the first and second dimension retention time. Again, this is for lumped compounds or unknown structure. And here are just some examples. So the type refers to my list up above, right? So you have this formula. If you have, the case of camping, you know what it is, you can assign an INCHI. We have monoterpenes broadly, we don't know what monoterpene it is. So it's given the exact mass plus the formula. Same thing here. Now this is an unknown C4H50. We can't assign it to a compound or compound class, but we can give it an ID. And then this would be the 2DGC example formula. These are a group of isomers. And so it's just the first and second dimension retention time. Okay, so a little bit about the data processing. So in the legacy and raw databases, all of the data are as they appeared in the source publication. When we moved to the primary database, we unified the formatting, but we also did some data correction steps. So, I would say that we corrected for known biases or artifacts, updated metadata, and a couple examples of that are here. So in the Akagi paper, there was a peatland category. We did not include the peatland data with peat. This includes the overlaying vegetation. So we took that out, right? As that's really a combined measurement and not just peat. In addition, the EFs from Akagi that had unknown pit masses, those were not retained either, right? So we kind of did some filtering and processing of the data. An example from the raw database, right? So these are newer publications. This is a paper by Abby Koss. The emission factors and costs were calculated assuming 50% carbon in all fuels. We did a correction to reflect the fuel-dependent percent carbon that was reported later by Selimovic, right? So this is the type of data processing that we did as we moved all the data into this primary database. In addition, for studies where there were multiple fire types of the same type sampled, we only retained an average. So if you sampled, garbage burning 30 times, we presented the average in this primary database. Moving from the primary database to the integrated data set. Now, this is a single data table with EFs for all compounds and constituents in all fuel types. So the idea here is that we are just building a single database. So we're adding rows, which represents new compounds or constituents, and we're adding columns, which represent the individual emission factors measured. And we need to be able to identify matched and unmatched compounds. And so when do we have a new compound or when do we have a new emission factor? And this is really when we started to use those unique IDs. The IUPAC matches and single constituents are easy. These grouped and unknown, sorry, typo, are a little bit harder. but I'm just going to give you an example of the sort of the second step of the algorithm. So we've matched all the IUPACs, that's easy. Here is an example. We have a single fuel or fire type, and we have these two hits. We have this compound, they have the same chemical formula, they do not have the same name. They come from two different sources, but based on their identification, we can actually tell that they are the same compound. So we combine these in the database. So we determine that these are actually the same compound. And again, I don't have all the data steps, but this is just to illustrate, or all the steps of the algorithm, that these are now combined. So instead of having two compounds here, which would be double counting in the database, we now have two emission factors. So we've increased the sample size, which is a pro, and we've reduced the double counting in this step. Okay, this is my last slide of the data processing. When we move from the integrated data set to the recommended data set, here we have a single average EF for each compound or constituent in each fuel or fire type. The final size of that table is 1,300, approximately 1,300 rows. So that means individual compounds or constituents, and 274 columns. So that has represented a single value has been represented up to 274 times across all the fuel or fire types. And some of the data processing steps, again, so we can have higher sample size. We converted the NOx EFs to NO equivalent EFs if NO and NO2 were available. We assigned fractional contributions to grouped compounds. This is probably one of the harder things to explain. I'm going to do it briefly, but if there's questions at any time, I can come back to this, or someone can talk to me about this offline. But basically, one of the advantages of 2DGC is that we can identify structures and mixtures, right? We have better separation. Quantification is a bear, but we have better separation. So, for example, this peak, right? If you're using PTR, for example, these compounds can't be separated, and crotonaldehyde and 2-butanol are synonyms, so they're the same thing. But so you have this situation where you have all three of these compounds were reported, you know, it's the sum, and sometimes that mass can get split either among these equally, but you know, it's hard to then figure out what to do with this when you're trying to model it. So we have this situation now where we actually have an individual measure of butanol or crotonaldehyde from another publication, and we have measurements of these two compounds from these two publications. Again, this would be, of course, in a single fire type. And what we do is, if the sum of these individual compounds are within a factor of 2 of this total, we use the relative distribution of these individual compounds, and we fraction, you know, we assign a fractional contribution. So now, again, we now have 3 individual compounds, easier to deal with in chemical sense, and we've increased the N. Okay, so that was what we did there. Finally, one of the other things we did, we adjusted the laboratory-based non-methane organic compound, EFs, to account for known differences in combustion condition. The correction is done for each fuel or fire type. And basically what we did is, for the smoldering dominant compounds, the lab-adjusted emission factor was calculated by taking the average of all emission factors to CO, right? So the average emission ratio for a given study, and multiplying it by the field CO. So this is basically, yeah. Go ahead.
2 minutes left. Sorry, just letting you know.
Oh, you're kidding me. Okay. Time, I have no clock. Okay, here's what I'm going to do. I am going to skip. Thank you so much. One thing, okay, I really don't have that many slides left, but one thing we did is, this is talking about the mapping, but I want to get to then showing you what this looks like. And I'll skip. Okay, so I'm going to start here. So here we have PM 2.5 emission factors from Akagi and Green, Andre and NEIVA. And so we see that, the PM 2.5 emission factors, I don't want to get into details, but we have compared them. PM 2.5, I would say, is relatively well constrained. When we add things like laboratory emission factors, we do get some differences, but this is an example of what we get. I think, again, because we focused on non-methane organic compounds, this is where things get more interesting, right? This is a figure of the number of compounds that we have in each of these fire types, right? So we have up to 800 compounds in the temperate forest because we've added the lab data. These on the bottom show the total emission factors, non-methane organic emission factor, total NMOC emission factor across fire type. And really what we've done is these hatched in the Akagi and Andre is an assumed EF, saying we know we haven't identified everything. We've really reduced the uncertainty there. And in some cases that's resulted in a reduction in the overall total emission factor. I'm gonna go ahead and skip those figures, because what I'm going to show you again, we've increased this N. So for example, comparing to Andre, in temperate forest, there's 89 overlapping compounds, and the sample size has increased for 75 of the 89 compounds. The list of compounds here are where we've increased the sample size by more than 5. Right? So again, we're adding data, reducing uncertainty for individual compounds. We've compared with WECAN and FireX. These differences have to do with, I think, the fact that we're including lab data, which is fresh smoke. We match better with FireX. There's a suggestion that FireX was sampling fresher smoke, and WECAN more age, so I think we have higher emission factors. I'm going to skip this, but I want to show 2 more slides if I have time. So one is this distribution in volatility, right? So if we map these compounds in volatility space, moving to the left, we have lower volatility. These distributions are very different. So the volatility distribution is influenced by the level of chemical detail, and this influences partitioning, it influences deposition, right? It has these distributions behave very differently in a model. Finally, when we look at when these compounds are mapped to their surrogate model species, again, if you just look at the height of the bars and the different colors, right, this is not the number of compounds, it's mole fraction. So we get really different distributions, and that has implications for chemistry. So this is probably the last slide that I feel like I need to show. And this shows the OH reactivity. So again, you have the same amount of non-methane organic compound total, but this is how it's distributed based on the measured compounds. And you get almost double the OH reactivity using the NEIVA distribution than you do from Andre. And this is an example with EPA speciate for crop residue. Okay, so we really are getting a difference in the OH reactivity in a box model. I will say we don't know at what scales this we don't know yet how this influences, at what scales is this important in a 3D context, I want to say. So I'm probably out of time. I want to say that we've been really inspired by the SARA database. The differences, of course, are that it focuses on North American fuels and has limited speciation of non-methane organic compounds. But we have built a prototype web interface for NEIVA. Right now, it's just in GitHub. We have to get this to peer review, I hope this week. And we're interested in, we're going to flesh out this interface for it. And there's a couple other things that I want to do, but I'm just going to leave it at there. And thank you for, sorry, I went slow at the beginning. I always do that.
No worries. Thanks a lot for that, Kelly. And because you started a little bit early, I think that's fine. We still have time for some questions. I see that Mark has a question in the chat there. I don't see anybody with their hand up yet. It's always great when people can ask their own questions. But Mark, would you like to ask your question?
I was going to make you work, Tim, but yeah, I can ask. Yeah, hi, Kelly. Thanks. This is really great presentation, and exactly this kind of things we're looking for in Burn. This is really going to be driving our uncertainty chasing for the next few years, I think, or one component of it anyway. But I just wanted to ask, because you mentioned or you skipped over the slide on the how much complexity we need. Yeah. It just made me think, would it be possible, could you comment on, or if you have any thoughts on mapping these very detailed level of emissions and speciation for applications in chemical transport modeling or even air quality forecasting?
Yeah, so so this is the slide that you're referring to. So we just said, okay, we have to be able to represent 90% of the total NMOC, right? That's just a random number, but it takes over 200 compounds to do that for temperate forest, and just under 175 for peat. And so I don't think we need to represent every individual compound. I think to start, we do need some measurements of these compounds across different ecosystems. We have that for a lot of ecosystems, but we need them for others. But then it's just making sure we do that mapping, right? And then we can, I think, as we've started to do here, as long as we take this information and map it to the model surrogates, that's a huge step. I think the other thing, though, we need to do is that we need to change the properties of the surrogate compounds. We have another paper that's coming right behind this one, where we've changed like the weighted OH reactivity, for example, to specifically represent the distribution of compounds in fire emissions. So I think we just have to acknowledge this information. We can still, I think, use our sort of condensed model frameworks, but we have to make some changes. And we may have to add a species or two. But I think we can do that with the computational power we have these days.
Thanks. I still don't see any hands up, but there's a question in the chat from Guido. Would you like to ask that yourself, Guido?
Sure. Yeah, first of all, I mean, thanks for all this really exciting work. It's really nice to see it. It's being, put together in a really comprehensive way and structured. Just one thing that I noticed, like for the PM2.5, that's what you show here. I mean, there's quite a big increase. And I guess because this database builds on earlier one where you average everything, do you know why it's the emission factor is so much higher, for example, in tropical forests, but also other types of burning?
So the PM is probably one of the hardest, I think the hardest things to reconcile. I mean, there's a couple things happening, and we've broken this down, but I didn't show it here. So one is that when we include lab studies, we sometimes have higher PM2.5 emission factors because the loadings are so high that you have additional condensation of really, so you sort of overestimate PM, and I think you underestimate non-methane organic compound, right? So this is one of the things that happens in the lab studies. And sort of similarly with the field studies, depending on how much dilution, right, where were they measured, there's a suggestion, for example, that, for a while we really underestimated the temperate forest emission factors. So like the temperate forest, Bob would just tell you that these numbers in the 20s, for example, or approaching 20 are much more realistic, and they were just unreasonably low originally. So it's a bit of a combination of, being able to sample closer to fires, and the lab data. And so we are being careful, and we are trying to assess this carefully in terms of the lab data that we're adding so that we don't push these artificially high.
Can I ask a follow-up question, Tim?
Yes, please.
Because it's also a little bit something we're struggling with, like how representative are different studies. And for example, if you have a Firex container, for example, you have a huge fire complex, you take that as one emission factor, and then you have a laboratory study. Is there any thoughts about weighing different studies that some are more representative than other ones?
We had a lot of discussion about that, of how to weigh. I don't know. I really think that what we need to do is try to think of reference points, right? So you have maybe some NO, NOx level, you have some CO2, and you have like a reference PM that accounts for some level of dilution and aging. I mean, this is something I've thought about because, yeah, there's just, in my opinion, there's pros and cons to lab and field.
Cool, thanks.
There would be time for one more question if anybody has one. Question. It's nice to see the strong focus on the highly speciated NMVOCs in this approach. And I'm wondering how the NMVOC emissions that you get in your inventory would compare with the NMVOCs from the kinds of inventories that we heard about yesterday, where I think it seemed that there was a speciation applied as a sort of a post-processing step based on a total NMVOC emission. You showed the slide compared with the Andre emission factors. Is that the same sort of difference you would expect to see between NEIVA and the other inventories we saw yesterday?
Yeah, so I mean, what I felt like was some good news here is if you focus on just this bottom panel for a minute, we didn't like blow up the NMOC totals, right? So the total NMOC, I mean, when it's a little bit scary when you look at the top and you're like, okay, we went from 200 to 800 compounds, right? So what happened here? So the total NMOC might not change that much. I mean, you do see some differences between Andre. Like, I think peat, we added a ton of peat data. I feel like our total NMOC from peat is better constrained than these other inventories. But if you look across, like for temperate forest or chaparral, we didn't change things that much. But really what is different is then how that's, mapped to the other compounds, to the model compounds, and how chemistry then happens in the models. I think that's where it makes a big difference. And again, I think there is still some work to do, though, to figure out at what scale, right? If you're doing global modeling, you don't need this, right? So I recognize that I think we just haven't been able to test like what scale this is important.
Thanks a lot for that again, Kelly. I think we can move on to the next speaker now.